Hello, everyone. Welcome to our chat room with Dr. Grissel Santiago. She will be with us answering questions from the audience on her presentation on 3D bioprinting. Thank you so much for being here with us. I hope you're enjoying our event so far. Hello, everyone. Welcome to our chat room with Dr. Grissel Santiago. I would like to give a special welcome to Dr. Santiago. It is such an honor having you here with us today, talking about such an interesting topic. Our commission team is very excited to have you here as well, and we thank you for your acceptance. Dr. Grissel, please let us know when you're ready to answer questions from the audience. If you have anything else you want to share with us, feel free to open your mic and your camera. Thank you. We shall patiently wait. Dr. Grissel will be with us shortly.
Hello, can you hear me?
We shall patiently wait. Dr. Grissel will be with us shortly.
Hi, can you hear me?
Hello, Dr. Grissel. We can hear you fine.
Can you hear me?
Patiently wait. Dr. Grissel will be with us shortly.
Sorry, I think I have trouble with the audio because I hear recordings like...
Hi, can you hear me?
Sorry, I don't know what is happening.
Maybe, are you watching the presentation on Even 3? Yes, maybe you can pause that. We have a small delay on there. Maybe that's why.
Yes, that was the problem. Thank you, Daniela. Now everything is working.
Okay, thank you so much for being here with us once again. Let us know when you're ready to answer questions from the audience. We have quite a few. If you have anything you want to share with us before that, feel free to do so.
Perfect. Yes, I'm ready. Thank you for the invitation. I'm very happy to be here.
Thank you for being with us today. Okay, so we can get started with the questions. The first one is from Dr. Luciano. He says, thank you very much for your amazing lecture. Dr. Santiago, the concept of chaotic 3D bioprinting is fascinating. Could you explain in more detail how to use how the use of chaotic print head contributes to the efficient and reproducible creation of layered structures in chaotic bioprinting?
Yes, of course. Thank you. Well, what happens is that chaotic flows are deterministic, so you can actually mathematically model them. And well, the printing heads that we use are, if you use exactly the same configuration, you will always have the same structure. And you can predict that beforehand to understand how the layers or the materials that you are printing are going to be accommodated within the filament of hydrogel previously before making the experiment. So it's really not it's what I want to convey here with this idea of having efficient and reproducible creation of layer structures is that we don't have to think about chaos in this context as something that is disorder or is not predictable, because these are the chaos. This is the chaos of the physics that you can mathematical model it. So I don't know if that is clear enough now, Professor Luzuma.
Yes, thank you so much for your answer. I really enjoyed your presentation, especially because when you compared the chaos to real life things that we can actually picture, it's actually really easy to understand that way. Thank you for that. We have another question for Carla. From Carla, she says, amazing lecture. Thank you very much, Dr. Santiago. Have you tried to do co-culture using this technique? Would be possible to arrange different cells in specific regions, creating a more complex system? And then she also says, which imitation does this technique have?
Thank you very much for that question. Yes, that is something that we are actually working on right now, using different cell types within the exact same structure. So far, we have done experiments in which we co-culture other types of cells, bacteria cells. And we have seen, because it's a more simple model, right? So we have seen that when you culture a probiotic bacteria and E. coli, which is a commensal bacteria, the interface, meaning the size of the layers that they share, the interfaces that they share, they behave differently depending on how close or how far they feel each other. So, and that is something that is very interesting for us. For example, if we want to produce probiotics where we have communities of bacteria sharing the same space, but not all mixed, but structured in a single volume. So we anticipate that we are going to see very interesting results also when we co-culture mammalian cells. We are now trying to co-culture muscle cells, myoblasts, and Hubeck cells that we aim to form endothelium. So we can have like a not pre-vascularized tissues, but vascularized tissues. The channels that you saw that are empty, they can be lined with endothelium tissue. So that is the first co-culture system that we are working on. But yeah, in the future, I foresee that we can incorporate neural cells and fat cells and the stromal cells. And so that's the idea behind of making this, pushing the capabilities of this technology to incorporate more materials and more cells. And regarding the limitations, well, there are some related to the materials that we can use. The materials that we can use with chaotic printing should behave as Newtonian liquids. So if we use non-Newtonian liquids, for example, collagen, it's hard to print with chaotic printing. You're not going to have these beautiful arranged lamellar structures as you saw with Gelman alginate, because Gelman alginate, under the conditions that we use to extrude them, they behave like water, like Newtonian liquids. So we have to, it's not impossible, but we have to fix some parameters to play with the extrusion times, to find, if we want to print different materials, they have to flow together. So there are, in the case of the materials in which we form the channels, the first approach was using pluronic acid with our bioinks with cells, but that combination didn't work very well, so we have to find another sacrificial material. In that case, hydroxyethyl cellulose worked very, very well with the cells and with all the components of the bioink. So yeah, there are some tricks that we have to play with so we can have those structures within the same filament. So those are the limitations so far, which is not a limitation, it's just something that is tricky that we have to fine tune to make it successful.
Thank you, Dr. Santiago. That is fascinating work. I'm very excited to see where the future goes. Dr. Luciano has another question. He says, the resolution achieved with the chaotic bioprinting reaching 8 micrometers is remarkable. How does this technique compare to the other extrusion bioprinting methods in terms of resolution and its ability to guide cell alignment and tissue formation?
Well, that is a very exciting question. And well, probably it's going to sound very bold, but you cannot reach 8 microns in resolution with other extrusion techniques. There are, as you know, some other techniques where you can focus electrons or not photons, sorry, not electrons, where you can make very fine structures using photosensitive hydrogels. But using extrusion, I haven't seen any other technology that can reach this structure. 8 micrometers is even smaller than a single mammalian cell. So for printing mammalian cells, we have to use less mixing elements, so we can actually have not a structured filament or not a very well mixed filament, as it will occur with 7 mixing elements, which is the setup that give us 8 micrometers in resolution. So this is very efficient if in making these sheets, and as you already explained, that is very useful for aligning cells. So in some experiments, what we have done is to put different materials, some of which the cells can recognize and others they cannot recognize, so they cannot cross the layers or the sheets, and they are forced to align towards the main direction of the filament. And we have tested and proved that this is an effective way of guiding cell alignment in 2 papers. Another one is coming. So yes, this is a very affordable and easy to use technology to provide those cues, physical cues for the cells to align. Thank you for that question, Professor Luciano.
Thank you, Dr. Grissel, for answering the question. We have another question from Dr. Luciano. Thank you for all the questions, Dr. Luciano. He says, in your talk, you mentioned the creation of hollow channels inside hydrogel filaments as a step forward vascularization. Can you elaborate on the process of creating these channels and how they contribute to improve cell viability and metabolic activity in the printed bioproducts?
Absolutely. Thank you for that very interesting question as well, Professor Luciano. Well, we can create those hollow channels also playing with the materials that we use and the cross-linking methods that they have. In the case of when we bioprint cells and we want to create channels, we use in the bioink GELMA and alginate. So alginate cross-link with calcium chloride and UV light, and we use hydroxyethyl cellulose as the fugitive material. So that one doesn't cross-link, is not going to respond neither to the calcium chloride or the UV light. So it remains liquid and it just leaches out, it drains out from the filament. And so that's the way that we can create those hollow channels. But this is the recipe that we have used. Of course, I'm sure that there are other materials that we can use to achieve the same result. And the process in which they, how this improve the cell viability and metabolic activity. So as we know, in our body, 2 types of transport occur: the convective transport through the blood vessels and the diffusive transport in the solid tissues. So our our aim in the future, we are not still there, but the idea is to perfuse media, so by convective transport, as it occurs in our blood vessels. We want to reinforce these channels because they are still not strong enough to support continuous flow of media, culture media through them. So we are now working on methods to reinforce those channels and allow this convective transport. But so far, the diffusive transport is also enhanced because of these porous structures that we have in these volumetric filaments. So what we think is that the cells are showing higher metabolic activity and also higher proliferation or the expression of proliferation markers, and they are decreasing the expression of hypoxia markers because they are more nourished because of the transport that is enhanced with these hollow channels that we incorporate in our hydrogel structures. I don't know if that was clear enough.
Yes, thank you, Dr. Santiago. We have many questions here. The next one is from Andres. He says the inner channels created with this mixing tool during printing are are they actual channels or just chaotic inner spaces? I think they would be equivalent to those created as inner channels from the 3D model and printed with sacrificial materials. Moreover, could they help to guide neovascularization?
And thank you for that question. Well, they are actually channels. They are micro channels that are, if you will see the fiber in the cross section, the channels will be like um, layers going from one pole to the other pole in the same filament, and they run through the whole filament, following the very same structure that we see in the cross section. So they are true channels. So they are not porous spaces, or they are continuous and they follow the exact same structure. So yes, they are two channels. And the other question was, I think we went to those, sorry, to the sacrificial materials. Well, I don't know if I understood very well the question. So this is actually produced with sacrificial materials, as we have seen in other reports. The difference here is that we can accommodate up to 32 channels, micro channels of 20 microns in width, more or less, in a space of 1 millimeter in diameter. So our fibers are 1 millimeter in diameter, and we can place 32 continuous microchannels with the width of more or less 20 microns. So that's the difference with other reports that we have seen. And how they can guide neovascularization. Well, so far we haven't achieved neovascularization yet. The first step for us is to convince the Hubeck cells or the endothelial cells to line the walls of those microchannels, and then hopefully in some years from now we will see that the Hubeck cells can create neovascularization in the solid walls that they see in the same filament. So, but we think that this technique can guide neovascularization, but we haven't demonstrated that yet.
Thank you, Dr. Santiago. I think we have time for one more question. It is also from Dr. Luciano, and he says, the use of chaotic 3D bioprinting appears to offer significant advantages in terms of efficiency, structure, formation. Are there any limitation or potential drawbacks to these techniques that researchers should be aware of?
Well, I think I will say the main difficulty is that finding you have to find the right materials. You have to find the protocol to use the materials that you need to use. With Yelma and alginate, it works very well, and those are the hydrogels that most people use for making bioinks. But everyone knows that they are not the perfect hydrogels, and so you have to, if you want to use more complex, rheologically complex hydrogels, then the system is not going to cooperate so well as it does in alginate and Gelma, but it is possible to do it. It's just you have to develop that expertise to actually um, use this technology with other more complex materials. I will say that that is the main setback from the technology.
Thank you, Dr. Santiago, for answering all the questions. I wish we had more time, but unfortunately, we have to end our chat room here. We have many other questions. I just want to say how inspiring you are for your work and being a woman in science. I'm honored to be here speaking with you. We have many compliments. Lucio says something that I agree with. Coffee and science are great combinations. I agree. But we will be sending you the other questions through via email so you can answer. We'll get back to our participants. I just want to thank you on the behalf of our committee for taking your time to being here with us today.
Absolutely. Thank you very much, Daniela, and everyone for your attention and your very interesting questions. Enjoy the
Thanks,
conference.
Dr. Santiago. Bye. I'll see you next time.
Bye.
Bye. Thank you, everyone, for your time. I'll see you guys in the next lecture. Obrigada a todos pelo seu tempo e perguntas. Até a próxima palestra.